So in the last video, you were introduced to the idea of an equipotential. In this video, we are going to talk about field lines and equipotential surfaces for more complex electrostatic setups. So let's go ahead and get started. So let's go ahead and start with the coaxial cable. So you may not know what a coaxial cable does, but you almost definitely have used one before, because coaxial cables are what connect your television to a satellite of some kind. So if you have satellite TV at all, you probably benefit from coaxial cables. So in a coaxial cable, what we have is we have an inner conductor, which is in orange, and you have an outer conductor, which is going to be this black line here. So that's your outer conductor. And then on the inside of your coaxial cable, what you have is an insulator. So your two conductors are separated by an insulator of some kind. So for my coaxial cable, when I talk about field lines, what I'm going to do is I'm going to go ahead and use this head-on view of it. So instead of looking at the side of the cable, we're going to look at its face. So in the middle, I have my inner conductor, and then I've got my green insulator, and finally my outer conductor. And my field lines are actually going to go out from my inner conductor through the insulator to my outer conductor in the same way that they do, or in a similar way to my spherical, to my charged sphere. So here we go. There are my field lines, and my equipotentials are going to look like they do for a point charge or for a charged sphere. What I'm going to have are these nice circles that are concentric to both my inner and my outer conductors. So they will never interact with each other, they will never intersect with each other, and they also will not intersect with either of my cables. So for our last situation, we're going to talk about a point charge and a charged plate. So the key to drawing an accurate set of field lines for your point charge and charged plate is remember that the field lines are radial to the point charge, so that means that they are in line with the radius of the point charge, and that's when they're very close to the point charge. And then when we get to the plate, the field lines will be perpendicular to the plate. So let's go ahead and start drawing field lines. So we're going to go out of our positively charged plate and into our negatively charged point charge. Draw a couple more. And now that I have my field lines, I am ready to draw my equipotential surfaces. My first one is actually going to look very similar to my one for a regular point charge, and it's going to be just a circle around the charge. My next ones, however, are going to extend a little bit. So what we're going to have is we're going to have kind of these little concentric half circles, like so. And we can kind of picture them, right, continuing around. So there you have it, folks. Here are your field lines and your equipotential surfaces for a point charge and a charged plate. And one thing to note that you maybe can't see super easily on our diagram is, again, the centers of each of our circles are going to be farther away from the plate than our point charge is. And again, that's just going to be because of the nature of where the field is stronger versus weaker. So takeaways. The shape, first of all, you learned that the shape of an equipotential surface depends on the shape of the field lines. And you also learned that you are able to draw equipotential surfaces even for complex fields. So fields that are more complex than a point charge or two. So hopefully you feel very confident with equipotential surfaces, because it is now your turn to try out some problems. So go ahead and give it a shot. Happy solving!